Alrighty, howdy folks. Um, there is a section in chapter 6 about law of sines and cosines. I'll come back to it a little later. So let's get on with chapter 7, and section 1 is on trigonometric identities. How should I put it? To me, this particular section is quite possibly the most interesting and challenging one in the entire trigonometry class. This is so beautiful. If you can solve every problem in this particular section, you would actually learn how to pretty much think, and also you will come up with a certain way of certain thought process which will help you solve problems in just about any course. You take physics, you encounter similar kind of things. Okay, and you will see what I mean in just a second. First, trigonometric identities. There are quite a few of them. Some of them you have already seen, or pretty much you have seen all of them, I think. Let's see. This is courtesy my colleague Tommy Elliott. So I like how he presents this. He says different identities are at different levels. Level 1 means the original identity. Level 2 means derived from level 1 identities. Okay, so what does he mean by that? First, reciprocal identities. We certainly talked about this, right? We said cosecant is the reciprocal of sine. So cosecant theta is 1 over sine theta. Secant is 1 over cosine theta. This you know. And you also know this quotient identities, that is tangent theta is nothing but sine theta over cosine theta. Cotangent theta is cosine theta over sine theta. That's a simple, straightforward one. But then there are some things called Pythagorean identities. I'll pick these two, the sine square theta plus cosine square theta equals 1, and this 1 plus tangent square theta equals secant square theta, and prove them. But this is what they say. Sine square theta plus cosine square theta is equal to 1. And now, that's a level 1 identity. But from this identity, by doing simple algebra, we can come up with two more identities, as this 1 and 2 that you see here. Would you agree that if this statement is true, okay, if this equality is true, that is this identity, couldn't we subtract cosine square theta from both sides and come up with this sine square theta as 1 minus cosine square theta? Yeah. And guess what? You must memorize and remember not only the level 1 identity, but also these level 2 identities. Similarly, I could subtract a sine square theta and come up with this, the second identity from that, right? And 1 plus tangent square theta equals secant square theta. You got to memorize that. From this, you can derive the fact that tangent square theta is secant square theta minus 1 by subtracting. And secant square theta minus tangent square theta equals 1. That's another identity. And once you know this, once you know the tangent square part, the cotangent part is kind of similar flair to it. Instead of tangent, you have cotangent, and instead of secant, you would have cosecant, right? 1 plus tangent square theta is secant square theta. 1 plus cotangent square theta is cosecant square theta. So sort of like the co-functions go together. Cotangent square goes with cosecant square. Okay? And then the derived identities from that. And there are also these negative angles I pointed out a long time back. Only cosine and secant have the special property of cosine of negative theta being positive cosine theta, secant of negative theta being positive secant theta. Everything else, sine of negative theta is negative sine theta. and automatically its reciprocal follows the same principle. And similarly, tangent of negative theta is negative tangent theta, and cotangent of negative theta is negative cotangent theta. And you probably recognize some concept called odd functions and even functions, right? So you notice that cosine of negative theta is an even function because cosine of negative theta is cosine theta. In general, if f of negative x is equal to f of x, then such a function f is called even function. However, if f of negative x equals negative f of x, like the sine is, then we say that's an odd function. Okay? Graphically, an even function is symmetric about the y-axis, and the odd function is symmetric about the origin. Okay? All right. And then co-function identities. I'll go through them, but how seriously should you take them? Boy, maybe not that serious, but it's good if you learn them, and it's fairly straightforward. Sine always goes with cosine. Sine and cosine are co-functions. That means sine of 90 degrees minus theta or pi half minus theta is cosine theta. Similarly, cosine of pi half minus theta is sine theta. And tangent and cotangent, they go together. Tangent of pi half minus theta is cotangent theta. Cotangent of pi half minus theta is tangent theta, and so on. So take a look at these things. So secant and cosecant are co-functions. That means secant of pi half minus theta is cosecant of theta, and cosecant of pi half minus theta is secant theta. Tangent, cotangent, sine, cosine. That's why they're called co-functions, because they have this particular property. Cool. All right. Proofs of some of the identities. Yeah, let me prove that sine square theta plus cosine square theta is equal to 1. That means for all values of theta, that statement is true. And what is that? You remember in terms of x, y, and r, sine theta is y over r and cosine theta is x over r, right? Okay, if that is the case, sine square theta means this whole sine theta is being squared. Please pay attention to that part. When we say sine square theta, we actually mean the quantity sine theta being squared. The entire sine theta is being squared. Is that the same as sine of theta square? No, it is not. When we say sine of theta square, we are squaring just the theta and then taking the sine of it. But that's not what we are doing here. We are doing sine square theta, which means we are figuring out what sine theta is and then squaring it. Aren't both the same? No, they are not the same. Sine square theta would be completely different from sine of the quantity theta square. Okay, all right. So sine theta is y over r, cosine theta is x over r. So sine square theta would simply be this y over r, the quantity square. Cosine square theta would be x over r, the quantity square. So we get y over r, the quantity square, plus x over r. So isn't the denominator r square common for both of them? So we can easily add the fractions and we get y square plus x square over r square. But wait a minute. Isn't y square plus x square equal to r square? Yeah. Okay, so let's replace that y square plus x square with an r square. So we have r square over r square. That's equal to 1. Right? As desired. We were expected to prove that sine square theta plus cosine square theta is equal to 1, and we just did that. Right? Cool. Prove that 1 plus tangent square theta equals secant square theta. I will adopt a similar strategy even for this. That is, since tangent theta is y over x and secant theta is r over x, right? In terms of x, y, and r, would you agree that's what it is? 1 plus tangent square theta is 1 plus the quantity y over x squared. And so now this is 1 plus y square over x square. If we add those two fractions, we get x square plus y square over x square. But wait, x square plus y square can be replaced with what? Yep, you're right, r square. So we got r square over x square. Isn't r square over x square the same as r over x, the quantity square? But what is r over x? Secant theta. So I can confidently say r square over x square must be secant square theta. Is that what was desired? That 1 plus tangent square theta should be shown to be secant square theta? Yes. Right? That's the idea. So that's how you can prove these identities. These did not just come out of thin air, you know. Somebody actually went through them. Cool. And then this whole section is about proving different kinds of identities. Those are the identities that we're going to prove here are not something that you may need to necessarily memorize. Some yes, but most of them not. Okay. But how do you prove this? Well, one thing is start with one side and simplify it so that you get the other side. And also use algebraic techniques in simplifying, replace expressions with proper trig identities, and use algebraic techniques such as adding, subtracting fractions, cross multiplying, factoring, distributing, all kinds of things that you have learned with x, y's, z's, and those kinds of things before, algebraic techniques. And also when you find that, man, I have no idea how to prove this, then try changing everything to sines and cosines and then simplify, right, as a last resort. So let me, one of the things that will come in handy is this technique of just simplifying a given trig expression. So before we actually prove different trigonometric identities, let's learn how to simplify some of the trig expressions. Okay, sin x times secant x over tangent x, right? Can we simplify this? Yeah, obviously that's equal to 1, right? What? What? Yeah, I know. Sin x times secant x over tangent x is just equal to 1? Yeah. Let's see. Can we in fact show that? Method 1. There are two methods. There probably are more than two methods. There are multiple methods. And let me pick one. Write everything in terms of sines and cosines, right? So sin x, that's already in terms of sine. Secant x, let's write that as 1 over cosine x. Tangent x, hey, that's sin x over cosine x. So let's do that. So sin x times, I replace secant x with a 1 over cosine x and replace tangent x with a sin x over cosine x. So do we have sin x over cosine x being divided by sin x over cosine x? Same term on the top and the bottom, that's got to be equal to 1. Or in other ways, hey, divide by a fraction is the same as multiply by the reciprocal of the fraction. So that's what I'm doing, right? Cosine x, that's equal to 1. Ta-da! So this is how you simplify trig expressions. What's method 2? In method 2, I look at this and go, wait, I can leave the tangent x the way it is and just replace secant x with a 1 over cosine x. And now I have sin x over cosine x, that's tangent x. So I just end up with a tangent x over tangent x, that's equal to 1. Right? If you saw that even before you saw my way of solving it, more power to you. Right? Pat yourself on the back. Cool. Let's pick another one. Simplify the trig expression. Yikes. Simplify the trig expression. Sine to the 4x minus cosine to the 4x. Let me see. Obviously that's equal to 1 plus sine square x. Yeah, 1 plus sine square x. What? That whole thing just reduced to 1 plus sine square x? Yeah, I tried to do this in my head. Nope, just sine square x, not 1 plus, just sine square x. I'll show you how. One of the formulas that algebraic formulas that you will have to recall quite a bit here is, you remember a square minus b square, the difference formula? What is a square minus b square? That's a plus b times a minus b, right? So I'm grouping the first two terms, the sine to the 4x minus cosine to the 4x. And then I'm saying, that's nothing but, recall that a square minus b square equals a plus b times a minus b. Is sine to the 4x minus cosine to the 4x looking like a square minus b square to you? If you say, no man, this is a to the 4 minus b to the 4, come on. Well, yeah, you're right. For a second, let me say, this is looking like p to the 4 minus q to the 4. Would you be okay with that? Instead of calling a to the 4 minus b to the 4, I'll call it p to the 4 minus q to the 4. But what if p were to be replaced by a square? So p to the 4 becomes a square, the quantity square, which is, if we say p square is equal to a, we have p to the 4. If I replace p square with an a, then what happens to sine to the 4x? That actually becomes p square square, which is a square. So that simply becomes a square. Similarly, q to the 4 becomes b square. So this is in fact sine square x, the quantity square, minus cosine square x, the quantity square. Right? And so we can certainly write this as sine square x plus cosine square x times sine square x minus cosine square x, and leave this plus cosine square x alone. Right? Now you might say, why? Why did you do that? I did that because now you notice there is this sine square x plus cosine square x, which we have an identity that says that's equal to 1. See that? That's the idea. So you kind of think like a chess player, a few moves ahead. I have a to the 4 minus b to the 4. Well, I can write that as difference of squares, a square plus b square times a square minus b square. So that means I can write this as sine square x plus cosine square x times sine square x minus cosine square x, so that I can apply that identity sine square x plus cosine square x is equal to 1. So this whole thing just becomes 1 times sine square x minus cosine square x. And 1 times sine square x minus cosine square x, you distribute the 1, you get sine square x minus cosine square x plus cosine square x. And quite nicely, the negative cosine square x and positive cosine square x add up to 0, reducing it to sine square x. So that's what I said. I said initially that should be 1 plus sine square x because I was doing this, and for some reason thinking that it would be adding, but nope, so that's actually multiplying. So then I corrected myself and said you would end up with sine square x, and sure enough, that's what we ended up with. Take a good look at this though. Would you have ever thought that this complicated looking thing would just simplify to a simple sine square x. That's the beauty of trigonometry. Okay. Can I tell you a story? I was fortunate that I had a teacher who special tutored me. And because of his special tutoring, he didn't take a penny from me. This was back in India in 5th grade. And because of his special teaching, I learned how to solve all the problems in 6th grade and 7th grade while I was in 5th grade. And so when I walked into 6th and 7th grade, it's like there was nothing that I had not seen. And I breezed through those grades, taught my friends who were struggling with the material too. And then I got to 8th grade. Even in 8th grade, for quite some time, I was quite comfortable. And then we got to trigonometry. Even with trig, I was okay for quite some time. But when we got to these verifying trig identities, I was overmatched. I was like deer caught in headlights. Wow, how do I do this? And for the first time in a long time, I was really scared and started to actually question my own intelligence. Maybe I'm not as smart as I thought I was. And fortunately, I went to my brother, who was very understanding, my older brother. He said, these, don't worry about them. There's a certain kind of technique to this, and the more problems you solve, the more comfortable you will get. And he showed me some of these things. And based on some of his instructions, I was able to solve a few problems, and then my confidence started to grow. And then I actually started to relish these problems. They looked like puzzles. And then I became absolutely comfortable and became a fan of these problems. So, if you happen to struggle, don't worry about it. Just keep at it. What I will do is I will give you solutions to tens of problems, fully worked out solutions. The moment you attempt something and you don't know the answer, well, look at my answer. Look at how I did it. And one more thing is, there's not just one way of proving it. There are multiple ways of proving the same identity. So, at least learn one method, and then you yourself will become extremely confident in it, and you will start to enjoy this part. One thing you need to know is, in all these things, recalling the identities from the top of your head is the key. You must know the identities so well, so thoroughly, they must be on your fingertips. And that is precisely what you will need when you take physics. You must know all the formulas, left and right, and they must be on your fingertips. So when you see a problem, you go, wait a minute, what are the known quantities? What are the unknown quantities? What are the givens and what are the things that you need to find? Wait, are there formulas that relate these quantities? And then you should recall the formulas from the top of your head and then apply. Right? That is what this also requires. This is why you must take this section deadly seriously and enjoy it. Cool? All right. What else? Simplify the trig expression. Oh boy, let me see. Can I do this in my head? Yeah. I'm already seeing this as, what do I do? I think I would like to write cosecant x as 1 over sine x. When I do that, I get sine square x minus 1 on the top, by adding fractions. Sine square x minus 1, that's negative cosine square x, and yeah, I think we can go from there somewhere. All right, so sine x over 1 minus cosine x. Check this out. I had certain technique in mind right now, but then apparently when I was working this problem out, I had a completely different technique. So take a look at what I wrote and see if it makes any sense at all. Okay. What I did is I multiplied both the top and the bottom by 1 plus cosine x. Why? Immediately, the question that should pop up in here, why? Well, that is because, once again, notice, we have difference of squares here. A minus b times a plus b is a square minus b square. Earlier we used it the reverse way. We had an a square minus b square, which we wrote as a plus b times a minus b. But here we have a minus b times a plus b, which we will write as a square minus b square. That is 1 minus cosine square x in the denominator. And, okay, that's fine. But why? Well, here is where you need to recall the level 2 Pythagorean identity, which says 1 minus cosine square x is equal to sine square x. Where did that come from? From the original level 1 identity, sine square x plus cosine square x is equal to 1. So 1 minus cosine square x is sine square x. So when we do that, we can replace the denominator by sine square x. Now there's a sine x on the top and there's a sine square x in the bottom. So that means we can reduce this to 1 over sine x. Okay, 1 plus cosine x times or over sine x, right? Minus cosecant x. Okay, what else? Now look at this. Is this in the form of a plus b over c? What is that? A plus b over c. In that case, could we split this into two fractions, a over c plus b over c? Yeah. So why is that? Because let's do that and then I'll show you. That is because we recognize this 1 over sine x is nothing but cosecant x. Reciprocal of sine is cosecant. There is a negative cosecant x here. So this positive cosecant x and that negative cosecant x add up to 0. So we would be left with only this simple term, cosine x over sine x. But wait, what is cosine x over sine x? That's equal to cotangent x. Right? Now take a look at this whole thing. The first and the final one. Oh, by the way, I'm sure I must have mentioned this before. All these equal signs are absolutely vital. In mathematics, we put equal signs and say A equals B equals C equals D equals E, then A must be equal to E. Right? We have a chain of equals here, so that means the very first expression that I see here must be equal to this very final expression over here. So that is the simplification. Would you have ever thought that this whole complicated looking thing, that's just equal to cotangent x? And guess what? If you were actually fiddling with numbers, you're doing some engineering problem and then you end up with this big sine x over 1 minus cosine, and then you have to figure that quantity out for say some angle 35 degrees or some nonsense like that, and you punch it into calculator. Instead this one says Why did you sweat so much, man? The whole thing is just simply cotangent of 35 degrees. End of the story. Right? Cool. What else? One more thing. Yeah, there's another reason. The reason I just gave about figuring out for 35 degrees is a silly reason. There's a more important reason. When you get to calculus 2, you will learn about something called integration. If you are given with something like find the integral of this expression with respect to x, that's how the question would be phrased. Find integral sin x over 1 minus cosine x minus cosecant x dx. In that case, you may have a very hard time working with the integral as such. But if you recognize these identities and you can simplify this and say that's eventually equal to cotangent x, the integral of cotangent x would be much simpler. And that's why you must learn to do this trig expression simplification. Okay? Verify the identity cotangent. Now notice how the problems have changed. Up until now, we were being asked to simplify expressions, but now this is saying, well, I'm going to tell you that if you were to simplify this, you will get 1. But show me that in fact that is the case. Verify that that is in fact true. Right? And here is where typically you take the strategy that, well, I'm going to pick a complicated side. There is a left-hand side, which is this, and left-hand side of what? Left-hand side of the equal sign. So there's a left-hand side and there's a right-hand side. So pick up the left-hand side, LHS, and see if you can simplify this. And always keep in mind, as you are simplifying this, your objective is to get the right-hand side. Okay? So always keep that in mind. That was one of the instructions from my brother. Always keep track of the other side. Keep in mind what it is that it is. Okay. Cotangent x secant x over cosecant x. As such, I don't get any ideas, but I'm thinking, yeah, just go ahead and change everything to sines and cosines. That is, cotangent x is cosine x over sine x. Secant x is 1 over cosine x. Cosecant x is 1 over sine x. Cool? Now, sine x and sine x cancel out. Cosine x over cosine x is 1. And so 1 over 1, that's equal to 1. Right? If you do not see that, that's okay. At least, would you be able to say that this cosine x over cosine x, they cancel and you're just left with 1 over sine x on the top? Is 1 over sine x over 1 over sine x, the same expression a over a, isn't that equal to 1? That's it. And that's equal to RHS. So look at the proof. Left-hand side equals this. Manipulate it and get something and show that that is in fact equal to the right-hand side. Cool? I picked a fairly simple problem to begin with, but slowly they'll get a little more complicated. All right. Tangent x over cosecant x is equal to 1 over cosine x minus 1 over secant x. Okay. Again, what's that American expression? There are more than one ways to skin the cat. To which I typically add none of which the cat likes. Right? The last thing a cat wants is to be skinned. So tangent x over cosecant x equals, how do we do this? There are multiple ways. One way is to pick the right hand side because there is a subtraction of fractions going on. So perhaps going ahead and doing the subtraction may be of utility. So we'll pick that. And then 1 over secant x is just cosine x. So 1 over cosine x, the quantity, minus cosine x becomes 1 minus cosine square x over cosine x. Are you okay with that one? If those of you who might have trouble adding, subtracting fractions want to think of this as cosine x over 1 and the least common denominator is cosine x and do it that way, you will find that this is 1 minus cosine square x over cosine x. The moment you see 1 minus cosine square x, you should recall, that's sine square x. Cool? So we have sine square x over cosine x. Got it? And here is where, notice, you should always keep in mind what it is on the left hand side. We are at sine square x over cosine x, but the left one has a tangent x. Wait. Tangent x, isn't that equal to sine x over cosine x? Right? So sine square x can be written as sine x times sine x. You agree with that? A square can be written as a times a. So sine square x can be written as sine x times sine x, and one of those sine x's, let's pair that with this cosine x, and that just becomes tangent x. Cool. Okay. I get tangent x, but there's another times sine x still left over, right? So do you see that? It seems like at this stage I can go to tangent x times sine x effortlessly. So tangent x is already here, so that's good. But we need to have a over cosecant x, but we have a sine x, right? Sine x over cosine x times sine x, like I was talking about. So this is tangent x. Oh, wait. Sine x is nothing but 1 over cosecant x. So let's replace sine x over cosine x with a tangent x and sine x with a 1 over cosecant x. And guess what? We're done. Right? That's equal to tangent x over cosecant x, and that's what our left hand side is. See that? I don't know if you find this to be what's the big deal, man? I got it. Oh, awesome. But if you didn't and this thing is like going over your head, don't worry. I'll try to help you out, and you need to work very hard too. Okay. Tangent x plus cotangent x is equal to secant x times cosecant x. All right. How should I put this? Okay. This may not apply every single time without fail, but to a large extent. One strategy to solving problems like this is this. You are better off taking the addition, something plus something, and working with it so that it becomes something times something. That's much easier. Going from addition and showing that to be equal to some multiplication is much easier, especially when you convert things into fractions. So in order to go from tangent x plus cotangent x to this, well, write that in terms of sine x and cosine x. Okay, so we have fractions. Add the fractions. Cool. How do you add the fraction? Well, common denominator is cosine x times sine x, right? And then that top becomes sine square x plus cosine square x over cosine x sine x, right? Immediately, what should you recognize? Hey, that sine square x plus cosine square x, there's an identity that says it's equal to 1. Great. So use that and say that is 1 over cosine x times sine x. Again, the right hand side, keep an eye on that. That shows secant x and cosecant x. But we have cosine x and sine x 1 over. Ah, come on, that is silly, right? 1 over cosine x is secant x. 1 over sine x is cosecant x. So, am I allowed to write this as secant x cosecant x? Because maybe I'll be more precise. I could have added one more step for clarity. Am I allowed to write this as 1 over cosine x times 1 over sine x? What would happen if I did that? 1 times 1 on the top, which is equal to 1. Right? So 1 over cosine x times 1 over sine x, but 1 over cosine x is secant x, 1 over sine x is cosecant x, and that's the right hand side. Cool? So typically addition needs to be shown to be a multiplication. You pick the addition side, have fractions, and then work with adding the fraction or subtracting the fraction and simplify. Okay, cotangent x minus cosecant x times cosine x plus 1. Okay. To me, whenever I see this, maybe I'll put it in the form of a question. Does it make sense to pick up the right hand side and somehow showing that is equal to the left hand side? Sine x, all we have is negative sine x. What can you do with it? I don't know. You can do a whole bunch of things, but especially with the focus being on showing that to be this, I think that was much harder. However, the more complicated looking left hand side, we can show that, maybe if I simplify this, I end up with negative sine x. That's how I'll prove it. That seems to be a more sensible strategy. Right? Okay, let's look at this. Somehow, as soon as I see a problem like this, I'm thinking cosine x plus 1. Okay, that's fine. But I have a cotangent x minus cosecant x. That tells me, wait a minute. Immediately in my head I'm going, cotangent x is cosine x over sine x. Over sine x. The denominator have a sine x. Cosecant x is 1 over sine x. Denominator is again sine x. So this has a denominator sine x, and so does this, same sine x. Okay, that's what I'll do, so that I can easily subtract the fractions. So that's my thought process. And what happens? Cotangent x minus left hand side is what I pick up. And like I said, write this, and the denominator is the same, sine x. So this simplifies to cosine x minus 1 over sine x. Right? Good. Where do we go from here? Hey, and also, the moment I see this, cosine x minus 1 and a cosine x plus 1, to me that's the a minus b times a plus b, difference of squares. Aha, so that's going to be cosine square x minus 1. What did I do? I know why I did that. Okay, fine. So if we multiply these directly, cosine x minus 1 times cosine x plus 1, we get cosine square x minus 1. Wait, isn't there an identity that says, yeah, but that identity actually says 1 minus cosine square x is sine square x. Are you with me? The identity says 1 minus cosine square x is sine square x, but here we have cosine square x minus 1. So what do? We'll say, okay, we can factor out a negative and write that as negative of 1 minus cosine square x. Right? So that just becomes negative sine square x. And that's one way. Here what I seem to simply do is recognize that, and as a result I factored out a negative out of the top, so that the top becomes negative 1 minus cosine x. Now I can multiply the tops and say that's 1 minus cosine x times 1 plus cosine x is 1 minus cosine square x. A minus b times a plus b is a square minus b square. And 1 minus cosine square x is sine square x. Sine square x over sine x is just sine x. And we have a negative which we are carrying, which we are making sure that we are carrying every time. And that reduces to negative sine x. Cool? See how clever you need to be? I got a few more problems on this one. 1 plus secant square x is equal to 1 plus tangent square x. There are many ways of doing this, but I don't know how I did this. Right now, as I look at it, I'm thinking, that should be a piece of cake. Because there is an identity that says 1 plus tangent square x is secant square x. So this becomes 1 over secant square x plus secant square x over secant square x. Secant square x plus secant square x over secant square x is just 1. 1 over secant square x is cosine square x. Yeah, done. Piece of cake. How did I do it? Okay. Converted everything to sines and cosines. That's another way. So this becomes cosine square x plus 1 over cosine square x on the top, cosine square x plus sine square x on the top in the bottom, and cosine square x's will cancel. This is equal to 1, and that's equal to cosine square x plus 1. Okay, that's fairly straightforward. Take a look at that. In the meantime, let me sip a glass of water. Okay, verify the identity. 1 over secant x plus tangent x plus 1 over secant x minus tangent x. I like this problem. It is obvious that we would not be picking the right hand side and trying to show that that's equal to the left hand side. It's probably possible by being extremely clever, but a more straightforward method is to pick the left hand side and show that that's equal to the right hand side. And especially add the fractions. That's the strategy. Adding the fractions. What's the common denominator? This times that. Secant x plus tangent x times secant x minus tangent x. And when we do that, we end up with the secant x minus tangent x plus secant x plus tangent x on the top. Cool. Hey, that simplifies. That simply reduces to there's a negative tangent x plus tangent x. That just goes to 0. And so we have a secant x plus secant x, which is 2 secant x on the top. In the denominator, again, look at this a plus b times a minus b, the difference of squares showing up. So using that, this is nothing but secant square x minus tangent square x. So 2 secant x on the top and secant square x minus tangent square x in the bottom. Okay, That's fine, but we are supposed to show that to be 2 secant x. What? Hey, wait a minute. There is a level 2 identity that says secant square x minus tangent square x is equal to 1. Where do we get that from? The level 1 identity is 1 plus tangent square x is secant square x. So from that you can say secant square x minus tangent square x is 1. So we end up with 2 secant x over 1, which is 2 secant x. That's the right hand side. Cool? Whoa. All right. Our ability to solve this, show this, hinges on one thing. That is, do we know how to factor a cube plus b cube? Okay? The key to this problem is recalling the identity that a cube plus b cube is a plus b times a square minus ab plus b square. If you recall this identity, then this whole problem is fairly straightforward. Based on that, the top looks like an a cube plus b cube, so let's write that as sine x plus cosine x times sine square x minus sine x cosine x plus cosine square x. And then we say, hey, this sine x plus cosine x and this sine x plus cosine x in the denominator, that just is 1. Not only that, we have sine square x plus cosine square x. Can we add these two and say that's equal to 1 from the identity? Yeah, we can. So guess what? That's just sine square x plus, I'm being patient here, cancel these two out or divided these two and said that's equal to 1 and end up with this. And on purpose, I'm putting the sine square x plus cosine square x together first and minus sine x cosine x, so that this is 1 minus sine x cosine x. Cool? That's it, eh? So get busy and solve just about every problem in this one. Cool? Alrighty.